All right, let's get into it. There's this invisible network that pretty much powers our entire modern world, from how you find the nearest coffee shop to how a 747 lands safely. We're talking about satellite positioning. And in this explainer, we're going to pull back the curtain and see how it really works.
I mean, really think about it for a second. You pull your phone out of your pocket, and boom, a little blue dot pops up, showing you exactly where you are standing on the face of the Earth. It honestly feels like magic, but it's not. It's this incredible symphony of physics, heavy-duty engineering, and timing so precise it's hard to even wrap your head around. So how on earth does it all come together?
Okay, so first things first, let's get a really important term straight. Almost everyone, myself included sometimes, just says GPS. But GPS is actually just the American system. The correct universal term for all of these systems, and that includes Europe's Galileo, Russia's GLONASS, China's BeiDou, is GNSS. That stands for Global Navigation Satellite System. It's a huge, truly global collaboration. Now, to understand this gigantic planet-spanning network, it really helps to break it down into its three main pieces. Every single GNSS out there is built on these three fundamental parts, and each one has a very specific, very important job.
So what are they? Well, you've got the space segment, that's the satellites whizzing around up there. Then you have the control segment, which is kind of like the brains of the operation back down on the ground. And finally, the user segment, which, you guessed it, is all of us. It's your phone, your car, everything. Let's take a quick look at each one.
The space segment is just mind-boggling. It's this constellation of dozens of satellites orbiting thousands and thousands of kilometers above our heads, and they are moving fast. A GPS satellite, for instance, is booking it at almost 4 kilometers a second. It circles the entire planet twice a day. But the absolute key here is that their paths, engineers call this their ephemeris, are calculated to be incredibly stable and predictable.
But, incredibly predictable isn't the same as perfect. And that's where the control segment comes into play. This is a whole network of ground stations scattered across the globe that do nothing but watch the satellites. They track their health, their signals, their exact position. Then a master control station crunches all that data, calculates these tiny little corrections for orbit and time, and beams them right back up to the satellites to keep the entire system in perfect harmony.
And that brings us to the user segment. This is literally any device with a GNSS receiver chip inside. It's your phone. It's your car's navigation. It's a surveyor's high-tech equipment. All these devices do is listen for the signals being broadcasted by those satellites, and then they use some clever math to calculate three vital pieces of info: your position, your velocity, and the current time. Remember that, PVT.
So how in the world does your phone take these impossibly faint signals from space and turn them into that blue dot on a map? Well, the answer lies in this really elegant geometric principle. It's called trilateration.
Just picture this. A single satellite sends out a signal. Your phone picks it up and calculates how far away it is from that one satellite. Now, that doesn't tell you where you are, but it does tell you that you're somewhere on the surface of a giant invisible sphere, with that satellite right at the very center.
Okay, now let's add a second satellite. Your receiver does the same math, calculating its distance from that one, which creates a second giant sphere. So where could you possibly be? The only place you can exist is where those two spheres overlap, which narrows your position down from an entire sphere to a perfect circle. See? We're getting a lot closer now.
And here's the magic moment. A third satellite signal creates a third sphere. Now, the intersection of three spheres isn't a circle anymore. It narrows all the possibilities down to just 2 points. And one of those points is usually completely ridiculous, right? It's like moving at 10,000 kilometers an hour, or it's way out in space. So the system just ignores it. And the other point? Well, that's you. That's your location.
So 3 satellites give you a 3D position. That's all you need, right? Case closed. Well, in a perfect theoretical world, yes. But our world is messy. And this entire incredible system hinges on solving one massive problem. And that problem is time. This leads us to a really, really important question. If the geometry says 3 spheres are all you need to find a point, why does your phone always seem to need at least 4 satellites before it gives you a solid location? The answer to this question reveals the absolute genius of how this whole thing was designed. So here's the deal. The satellites up in space, they are equipped with these mind-blowingly precise multi-million-dollar atomic clocks. Your phone, on the other hand, has a cheap little quartz clock that, by comparison, is just
wildly inaccurate. And that tiny, tiny difference in time between the perfect satellite clock and your crummy phone clock creates enormous errors in the distance calculation.
How enormous are we talking? Get this. A timing error of just 1/1000th of a second, a single nanosecond, can throw your position off by 30 centimeters, or about a foot. So if your clock is off by just 1/1,000,000th of a second, the system will think you're 300 meters away from where you actually are. The timing has to be almost perfect.
And this is the brilliant part. That fourth satellite signal isn't for position at all. It provides the extra piece of data your receiver needs to solve for a fourth unknown variable, its own time error. It's basically an algebra problem. Your phone says, I have 3 distance measurements that don't quite line up. What time do I need to set my own clock to for all 4 of these measurements to converge at a single point? It solves for its own error, and in doing so, it synchronizes your cheap little clock to the perfect atomic time of the entire satellite network. It's amazing.
Because of that built-in clock error, the very first distance measurement your phone calculates isn't the real range. It's what engineers call a pseudo-range. Think of it as a fake range. It's a raw number that's full of error, and it only becomes the true range after that fourth satellite lets it fix the clock.
And, as if that wasn't hard enough, clock error is not the only problem. As these signals travel from space, they have to go through an obstacle course. They get bent and distorted by our atmosphere's ionosphere. They get delayed by weather in the troposphere. And once they get down here to the ground, they can bounce off buildings and mountains, creating an error we call multipath. The system has to constantly model and correct for all of this stuff just to give us that accurate blue dot.
Okay, so that's the how. It's incredibly complex, it's brilliant. But let's talk about the why. Why does this all matter? Well, it turns out that this technology has quietly woven itself into the fabric of pretty much every aspect of modern life.
You know, we all think of GNSS for getting directions in our car, but its impact is so much bigger than that. It is absolutely essential for aviation, for maritime shipping, for disaster response teams, even for scientific research. But some of the coolest applications are in fields you might never ever expect.
Take farming, for example. In what's called precision agriculture, that incredible positioning lets a tractor steer itself, planting seeds in perfectly straight lines year after year. It lets farmers apply fertilizer or water with pinpoint accuracy, only exactly where it's needed. This drastically cuts down on waste, on costs, and on the impact to the environment.
Or how about construction? Modern systems can now use super precise positioning data to automatically guide the cutting edge of a bulldozer's blade. They just upload a 3D digital model of the site, and the machine can grade the entire area to within a centimeter of the design without a single human ever putting a survey stake in the ground.
When you really step back and look at it, GNSS isn't just a cool feature on your phone anymore. It's become a true global utility, just like electricity or the internet. It is the invisible scaffolding that supports our global supply chains, our critical infrastructure, and our increasingly automated world.
And that leaves us with one last, kind of sobering thought. This whole world-changing system relies on signals that are incredibly faint, that are vulnerable to being disrupted, and that depend on countries around the world cooperating to maintain them. It works flawlessly day in and day out, until maybe it doesn't. So what would a day without that little blue dot really look like?